All right, y'all. Good afternoon. We have arrived in our last class. I mean, if you don't count the final. Like the final, I don't know if you count that class. But here we are. And it's just to be reviewed, so it's not maybe the most exciting thing, but, the thing that might, what I hope is as we go through this, just think back to the first day when we started class, and all these equations were new, unless you take an AP Physics before. But so much new stuff, and then as we go through this, one of the encouraging things is you can see how much you learn by just show this to some random person and say, does this make sense? And they'll probably feel the same way you did in the beginning. And so that's an encouragement, y'all. You've gained information, you've gained knowledge, you can do things that you previously could not. You will hopefully understand the world around you a little bit better. I mean, you all understand the world pretty well. I mean, you can walk and not run into things. You can drive and hopefully not run into things. But now you can hopefully predict things better and explain things better. And now that you all look at various things, cranes or roller coaster rides or whatever, you can look at it and understand all the details that go into it. It's not hard to make something that rolls. It's really hard to make something that rolls that's like 10,000 kilograms and do it in a controlled fashion. It's not hard. Y'all can just roll, you blow up a water like a balloon, and you can make it launch across the sky. That's like a mini rocket. It's really hard to make something that's a rocket where it's going again tens or hundreds of thousands of kilograms, going thousands of super fast. That's where engineering gets really interesting. It's either in making something really precise or doing something at scale, and you've got to know the physics. You can't build a skyscraper if you don't know the physics. Stacking a bunch of rocks on each other will only get you so far. I mean, the pyramids, they got them pretty far. But, if you want to build a building really thin, you can't just be building a block of blocks. So anywho, hopefully this is useful, entertaining. Joke for today is how many times can you subtract 10 from 100? Just once. After that, you'd be subtracting from 90. Nice groaning ones. There you go. A couple things I want to point out. I made announcements. One is that my office, first one that's most important is your free response grades are posted. If you didn't see that, they're very good, which is what I mentioned previously. The first problem, and fun fact, I'll show you this in a second. We're going to go through some of those problems today. One of them I didn't actually get to, but give it to you class. We're going to talk about it. Free response grades are posted. My office hours this coming week are extended. So I'm going to be available Monday and Tuesday, roughly from 10 to 1:30, 10 to 2, it's in the announcement. And then on Wednesday, I'll be free from 1 to 3. Stop by or don't. If you don't stop by, I'll do other things. So if it's helpful, stop on by. If it's not helpful, don't stop on by. Up to you. Yeah. Yeah, so the final is going to be 40 questions, multiple choice. And on the final, you can bring an entire sheet of paper, front and back, whatever you want. The idea is the final is twice as long as the other tests. If you take 2 5x8 note cards, it makes a full sheet of paper. And then I don't have 500 note cards. So. The multiple choice will be similar to the tests up to this point. So they'll be similar to the multiple choice you've had on previous tests. There might be a handful of problems, 5 at most, that are more involved, trying to fill the void of the response. But nothing crazy, nothing super long. In general, every problem I give you should be solvable less than 3 minutes or 4 minutes or something. They're going to take way less than that if you know what you're doing. Yeah.
Do you reuse problems from previous tests?
I do not reuse problems. They're all brand spanking new problems. Makes my life easy. Yeah, it's always to never want memorization to be the thing, and in the off chance people somehow memorize the problems and run them on the paper and all that whatever nonsense. So they're brand spanking new. But hopefully, like the previous tests, you'll look at them and say, I've seen a problem like this. It may look different, but you kind of know what to do. Yeah. Oh, yeah. Let me make a slide with that because I said in my studio class I would do that one. Yeah, so I did tell you all there's like one problem you know is going to be it's going to be a free body diagram problem because that was the one problem like everyone missed on test 1. So let me just chuck that in here somewhere. We'll just do it near the beginning. Where is it? Yeah, we'll put it after this. So I have some random problems in here. Here, I'm just going to put free body diagram problem. And then when I see this, draw a free body diagram. I'll be really confused, but I'll hopefully remember. For ... All right. So we'll go in order that we learn things. I'm going to kind of go through the so the same test reviews that we've used, we'll kind of go through those and I'll make up I say make up, I've already made up problems. And this is now where I'm also going to show you all something that you might not have realized, but it was here the whole time. And I knew about it, but I just didn't care. I'll just point it out and let it reveal itself. So if you go to web courses, the reviews for all the tests have been posted. Test 1 review, it's been available since the beginning of the semester. Test 2 review, it's been available since the beginning of the semester. Final review, it's been available since the beginning of the semester. I'm going to double confirm that. Yep, there it is. And then if I open this document, so this was kind of here all along. If you open this document and you scroll down, you actually see that the free response questions on the tests were actually here the whole time. At least variations on them. So this document actually had the free response questions from the last tests. And it was actually available on day 1 of the class, which is just interesting. And then you're like, why didn't... Well, I realized it after the fact, and then I kind of just had the thought process. If someone is so proactive that they're going to look at the final review that advance, then I'll give them the benefit of seeing the free response stuff. There you go. So anywho, this was here, and test 2, there's the pulley. There's that pulley problem is right there. Then, test 2, free response. There's the asteroid problem. There's the spring problem. So anywho, they were all here the whole time. It's just kind of funny. I have not, you can see when I uploaded this, August 14th. So there you go. Funny things. So we're going to go through these. The free response problems are good exemplars of things you need to know. That's why they're the free response problems. So we'll do those. But yeah, let's kind of just remind you all of what the heck you all learned in the first week of class. Vectors. And the rule of thumb is you got to break it into X and Y. If you're not BFFs with right triangles at this point, then you're going to have a rough time. Right triangles are our friends, big fans. You cannot combine vectors unless they're in X and Y. That's just how the cookie crumbles. And there's all your units, which hopefully you're familiar with. Now, speaking of vectors, let's go ahead and jump back over and practice that. Adding vectors mathematically is fairly straightforward, but one of the skills I really want you all to be capable of doing is here, and I want to, You know what? Let's make it different for you all. What is A plus B? Let's do 2A plus B plus C. So this is a more complex one, but y'all can do it. What does 2A plus B minus C look like? See if y'all can draw it. If you can visually add a vector, it lets you check the math. And it's really, really useful skill. And it's really easy to do once you, it's very quick. It's very quick if you know how to do it. So A is kind of up to the right, maybe about a 20-degree angle. B is down to the right, like a 60-degree angle, and C is down to the left, maybe 45-degree angle with respect to the negative x-axis. All right, so the magic sauce here, y'all, is tip to tail. So the way I'm going to do this is I'm going to cheat and actually just use the arrows. When I make these problems on tests, this is what I do to make sure the answer is right. So there's A. 2A is literally just A plus A. So we just make another A, and we put it there. Tip to tail, we just put one vector after the other. Then we take a B and we put it after that. And then we take a C, and subtracting a C is the same as adding, taking the x component of this, flipping it, taking the y component of it, and flipping it. Subtracting a vector is the exact same as adding a vector that's flipped 180 degrees. Because it just flips the x and it flips the y, it rotates it 180 degrees. Boom. That's once, that's twice. And so there, now what do we do with this? The final answer is we're going to draw a vector from the beginning to the end. So we're going to start here at the beginning, we find here at the end, and the answer is that big green line, and there you go. So, visually, it's adding all the x and y components for you, which is really nice. The height of this plus the height of this one subtracted by the height of B plus the height of C, ends up being the x and y components. And then, if I said find the x and y, you got that, you find the angle, all those good things. Don't forget how to do this. This is a bread and butter skill. Very, very important. Almost regardless of your major, any engineering, even software, vectors are like a thing that you kind of have to sometimes keep in mind. I've at least heard that, but don't quote me on it in terms of, because I don't know exactly what it shows. But vectors are super important. So anyhow, great. We did vectors. Woohoo. That's something that you all just need to be comfortable with. 1D kinematics. 1D kinematics, what's the relationship between position, velocity, and acceleration? Remember, it's take derivatives to go down, take integrals to go up. You want to go from position to velocity, derivative. You want to go from velocity, acceleration, derivative. And integrals vice versa. All are beautiful kinematics equations, which originally looked intimidating and unpleasant, and hopefully at this point you've realized they're just like a bunch of different Allen wrenches, and you just choose the right Allen wrench for the job. Given what you have, given what you need, choose the right equation. Honestly, this first equation, if you know that first equation, you can figure out all the rest. This first equation just says the final velocity is initial velocity plus acceleration times time. To go from the first equation to the third equation, you just integrate it. If you do the integral, you get the bottom equation. Take the integral with respect to time. It kicks a t in front of the v naught. Integral of t is t squared over 2. Ta-da, you get the third one. The second and the third, so to go from this one to the third one, it's just using average velocity, which is just the definition of average. Take two numbers, add them together, divide by 2. That's how you average something. Acceleration, if you average it, it works. That is pretty good approximation. Works out well. The last one comes from a bunch more algebra. Vx squared equals vi squared equals 2a delta x. That one's not as easy to explain where it comes from, but again, it's just another tool. Remember that on Earth, gravity is negative 9.8 meters per second squared. Nothing surprising there, hopefully. And then there's this question for y'all. A 10,000 kilogram spaceship is falling towards the moon. And it's free falling. It's free falling towards the moon. And a 50-gram bolt falls off the spaceship as it falls. If the rocket on the spaceship never turned on, which hits the ground first, they both start one flowing their way, and they're both initially traveling at negative 10 meters per second. I'll give you all 30 seconds. The answer to this is absolutely critical. If you all, this is one of those things, to solve this problem is, in my opinion, a very critical concept. I haven't quite been able to justify why, but in my head, it's important. Give you all a few more moments to think about this, how you would answer this, solve this, whatever. We'll write down our givens. M1 equals 10,000 kilograms. M2 equals 0.05 kilograms. They both share the same velocity. That's negative 10 meters per second. Their initial position is 1e3 meters. Their final position is 0 meters. Their acceleration I didn't give you, but it's on the moon. The acceleration on the moon is about 1/6 that of the Earth. So 9.8 divided by 6, which equals, I believe, like 1.67 or something. We're just going to say 1.6-ish. Something like that. Negative. What are we solving for? Really it's time. And, all this nonsense I wrote down is completely unnecessary, but it's just to prove a point. If you all go back to the kinematics equations, mass doesn't show up in any single one of them. And none of those problems do mass show up because everything accelerates the same due to gravity if there's no air. If there's no air, everything falls at the same rate. Air is the only reason things fall faster or slower than each other. And I've asked a question like this on both the tests. One, you can use kinematics to explain it. You can also use energy. So there was a problem in the last test about this as well. So you can do the kinematics equations and whatever, there's no mass. You can also do mgh equals 1/2 mv squared. The masses cancel. If there's no air resistance, there's no work, the mass cancels. And to me, this is just a really important idea that you all know. It's one of those things that most people, it's a very common misconception or preconception, is that things fall at different rates. And yes, that's true if air resistance, and that's the only reason. So it's just one of those, this is what the math shows us, and it's important. I don't know. To me, it's important. I don't know why. One of those just things that most people get wrong. That's probably why it's important to me. So there you go. So then that leads us into forces. So, okay, air resistance, great. If air resistance is a thing, then we might have to account for it. So we talk about forces. Oh, 2D kinematics. You got X and Y. Don't forget about it. So there's a problem in the last test of projectile motion. Super straightforward. I say super straightforward. It's a classic. So if we jump over to the test to review, we'll just quickly solve this problem. I'll at least remind you all of it and then see if that... I don't want to... Well, we got time. But projectile motion, someone throws a ball at an angle of 25 degrees below the x-axis with a velocity of 5 meters per second off a 30-meter high cliff. How far does it go? How high does it go? Just spend some time. You can either start writing things out or just like, do you know how to solve this problem? This is a classic, projectile motion is just a classic. So really, this problem is testing two things. One, can you draw your picture correctly? And two, do you know to split things into X and Y? That's really what it's testing. So this one says I throw at an angle of 25 degrees below the X-axis. If you drew your arrow up in the picture or you didn't realize it was pointed down, you're going to get the wrong answer. And the good news is that, we'll get to this. Part B, how high does it go, is a very easy answer. It goes 30 meters high. It's as high as it goes. But if your picture's bad, you're going to probably get the wrong answer. You're going to say it goes up instead of down, and that's wrong. So anywho, we have our initial velocity of 5 meters per second. You should immediately break this into X and Y. Do not wait. The X component, if we draw a nice little triangle here, this is my angle of 25 degrees. The adjacent side is the x component, so 5 times cosine of 25. And the other one's 5 cosine of... Oh, and be careful. This is where your picture might be good, but if you don't realize that the y component is negative, you will get the wrong answer when we ask how far it goes. Kinematics problems really do boil down to, can you split things into components, and can you assign positives and negatives correctly? If you mess up the positives and negatives, you get the wrong answer, and it's terrible and sad. And this is a multiple choice test. And you better believe that I will have answers that will be if you do the wrong process. When I design a test, I don't just make one right answer and then make up a bunch of numbers for the other answers. I make one right answer, and then I make generally 2 answers that you'll get if you do it the wrong way, if you make a really common mistake, and then maybe 1 nonsense answer. Yeah, so it might sound mean, but it's to make certain you're actually paying attention. If I just put 1 right answer and the rest nonsense, it'd be too obvious if you messed it up. And in the real world, no one's going to tell you if you mess things up until you test your thing and then it costs money or lives or whatever. So you got to get good at error checking because you can't. It's not a guarantee that someone's going to do it for you. Anywho, you all have seen me make enough mistakes. It'll happen to you. You got it. The more you do something, you don't really get. You do tend to make less mistakes. But really, you also just get better at catching your mistakes. All right. Something I want to point out here. I put my y initial as 30 meters and my y final as 0 meters. Sure, that's fine. But I want to also point out to you all, I could instead make my y initial 0 meters and make my y final negative 30 meters. That's also correct, and it will work perfectly fine. You could even get crazier, and you could put your y initial as 1 million meters, and then you just put your final as 999,970, as long as it's all about the difference. And this is a really, the reason I'm actually mentioning this is because when you all take physics 2, you're going to learn about something called voltage. Voltage is for charges what height is for mass. So when it comes to height, you only care about the final and the initial. You only care about where you start and where you end. Position is all relative, all that jazz. It's the difference that matters. I don't care if I start 1 million meters high. I care about how far I'm going to fall until I hit the next thing. I could be 1 million meters high and be perfectly safe as long as I don't fall 1 million meters. That's when it becomes dangerous. When you all get to physics 2, you'll learn about something called voltage. You actually have heard the word voltage. It's on your batteries. It's in what you plug a wall into. Voltage is the same like height. When you all have a 12-volt battery, it just means the positive terminal is 12 bigger than the negative terminal. So the positive is 12 and the negative is 0. Or the positive is 100 and the negative is 88. It doesn't matter. It's not saying that it's 1.5 volts. It's saying the difference between the 2 ends of your battery is that value. And that's a really important concept most people don't understand. It is actually perfectly safe for you to jump and hang on to a power line as long as you're touching both the same wire. Because if you're touching the same voltage, nothing's going to happen. If your height is the same, you're not going to fall. If your feet touch the ground and you're touching a power line, now you have a high voltage and a low voltage, and it will go through you and kill you dead. So the other case of that is a downed power line. If there's ever a downed power line, it's only dangerous if you take a big step away from it, because then there's a high and there's a distance and a difference between them. If you shuffle your feet, you're okay. Anyway, you often this is the thing. Electrical repairmen, they'll be in a helicopter and they'll just connect their helicopter to the power line, and they're fine because it's an isolated system and there's no difference in voltage, so nothing's gonna happen. Yeah, that's why birds are okay. They land on the power line. Power lines do not have insulation on them. Insulation's expensive and unnecessary. They're just bare wires up there, which is why if they fall, then it's a concern. But yeah, birds land on it perfectly fine because it's look, if I'm standing on flat ground, I'm not going to fall because there's no height difference. Anyway, things to keep in mind when you all take physics 2 at some point. All right, so we're trying to figure out how far it goes. We're trying to find XF. We're trying to find how high it goes, which is, 30. We did it. All right. So this problem, you go through the motions. You're going to find the time it takes because that's always a requirement. So you can have a great time and do yf equals y initial plus v initial yt plus 1/2 at squared. And you can do the quadratic formula because it's so much fun and we love it. I hate it. I avoid the quadratic formula at all costs. It's like a annoying sibling. You can love them, but you don't want to spend that much time around them. Quadratic formula, I feel that way. Or you can do vf squared equals v naught y squared plus 2a delta y, and then you can use that. So you can do two equations and avoid the quadratic formula. For me, at least, this results in less error. They're both fine. Neither one is bad or good. If your calculator can solve a quadratic for you, great. Do that. I don't really care. But we'll find the time. So I'm going to use this method, the second method, because it's just, I'm less likely to plug something in wrong. The quadratic formula is so particular. Negative b plus or minus the square root of b squared minus 4ac. There's so many opportunities to plug the wrong number in the wrong spot. So, anyhow, you do you though. I'm going to use these. So vfy squared is going to equal my initial velocity squared, so negative 2.11 squared plus 2 times negative 9.8. And I actually made this mistake this morning when teaching the studio class. I put my change in y as positive 30. And if you do that, it's going to spit out an error when you try to take the square root. Delta y is the change in y. Y final minus y initial. And it's negative 30. If you don't put it as negative 30, when you plug the square root of this number, it's going to be the square root of negative, and it'll kick out an error. It's nice when your calculator spits out an error because it tells you messed something up. You're not always so lucky, but in this case, it caught that, and I had to think about it this morning. These are the kind of mistakes that are easy to make, no matter how long you've been doing this stuff, so always be careful. So anywho, we're going to square that initial number and plug all that jazz, square root it. And you get the final velocity is 24.34, and that's not what we're solving for in this problem. It's just a stepping stone. We're then going to plug that into the purple one I'm going to make purple. So then we're going to do 24.34 equals, and this is where if you don't put the negative, things will go bad for you. You will get the wrong answer. And I can almost guarantee you I will put an answer on the test that would then match to the wrong answer. And really the only solution is, being careful, double checking, just being mindful of what you're doing. Time is 2.7 seconds. I'm going to double check my work to make sure I didn't plug anything in wrong. Oh, yeah. Okay, look, this is going to be wrong. Look, there's a mistake. Yep. And I noticed it because I was being mindful. My final velocity I put as positive, which says that when it hits the ground, it's going up. Nonsense. So this should be a negative, which will then make this a negative, which will change my answer. I didn't get lucky in the mistakes canceling out. So, again, super easy to make these mistakes. And it's a subtle difference. Well, okay, it's subtle. It's actually 0.5 seconds different. It's not a small difference. And the reason I realized this is I realized when I plugged in my calculator, I got a time that was negative. And that was nonsense. I'm not going to hit the ground negative 2.5 seconds from now. Like, that doesn't make sense.
Unless you reverse time.
Unless I go backwards in time, at which point, this does describe a parabola, but we're not going backwards in time in this case. So these are the kind of checks that you can do. If you get a negative time, it's nonsense. In our problems, I'm not saying what happened in the past. They're pretty much always what happens in the future. Though you could work in the past with physics, it doesn't really care. It's one of those reasons they consider time travel and all that. It's because according to physics, you can just change the sign of time and you now go backwards. All right, what was the whole point of this? The whole point of this was to finally find XF which is just going to be x naught plus v naught xt plus 1/2 ax t squared. There is no acceleration in the x direction, so get that out of here. So we get xf equals our initial position is 0. All this work. But there's lots of things we as humans launch or throw, and it's generally pretty good to know where they're going to end up and when. The reality is we live around a lot of defense contractors, and a lot of people from UCF get hired by defense contractors, and a lot of things related to defense are taking an object and making it go somewhere else really fast and hitting something, and you need to be able to predict that well. So it's a rough thing, but the reality, like however you want to view that, that is just a thing. Planes and all that stuff, you need to make certain your plane ends up at the right location. All those things. You can think of lots of cases why you need to predict where something's going to end up. So kinematics is the skills for that. All right, good time. Have fun with this one. If you can't do this projectile motion, it shows that something is off in your understanding of kinematics. This uses a lot of skills together. It uses like all the kinematic skills together, at least to the level that I am asking you to know. If this is really simple and you're bored and you're ever wondering, man, this is too simple, a problem I propose to you all that's an interesting one to think about is launch it from a ramp and then say, where's it going to land? And it's a really interesting problem. And the key to solving this problem is you have to parameterize y in terms of x. It's just it's a fun problem. Obviously I'm not going to have y'all do that. But the world ain't flat. The world ain't flat. And so, you can see how things get more complicated. So there you go. All right. Now we're at the one that forces, 2D kinematics. Woohoo. Forces. Oh, yeah, don't forget these things. If you're landing at the same height you start from, the total time equals time top times 2. If you're at the same height you started with, your final velocity is negative your initial velocity. At least in the y direction, dx is constant, x, y. If any of these things don't make sense to you, you should spend some time thinking about them because they're things that should make sense to you when it comes to projectile motion. So it's a good kind of checklist. You should not use the range or the height equations. If you've looked them up, you'll know what I mean. Unless you know when you can't use them. You should not use there's like specific equations that will give you the range that you travel and the height that you travel. You should never use those equations unless you know what cases you can't use them. Because the test ain't going to tell you. The range equation you can only use if you start and stop at the same height. The height equation only works if your angle is above the horizontal. Like that problem I last gave you, if you all try to use the height equation, obviously it's going to give you the wrong answer. Anyway, shortcuts only work if you know when you can use them. All right, Newton's laws. Forces. They explain why everything does what they do. Really, really great stuff. You all do need to know these Newton's laws. You don't need to have them. You don't need to know which one's which. I'm not going to ask you which of Newton's laws explains this. I'm not going to say I punch the wall punches back. Is that Newton's first, second, third law? I'm not going to do that. But I will ask questions, potentially like, the fly in the car. A car hits a mosquito. How do the forces compare? Asked that one forever ago. They're equal. Forces do not tell you what's going to happen. Acceleration tells you what's going to happen. You have to take the force and divide it by the mass to actually figure out what's going to happen. If I push something with 1,000,000 newtons, you have no idea what's going to happen until I tell you what I'm pushing. If I push the earth with 1,000,000 newtons, nothing's going to happen to the earth. If I push pretty much anything small, a car, me, you, whatever, with 1,000,000 newtons, it's not going to go well because the mass differs. So don't forget that. All those things. There's lots of random conceptual problems I've done with that. Always draw a free body diagram. Whenever y'all are actually getting to problems, anytime I say the word force, you should be drawing a free body diagram. Anytime I say the word force, if that shows up in a problem, you should almost guarantee you draw a free body diagram. almost guarantee you're going to be using it. There's a whole list of forces: normal force, friction force, tension force, applied force, force due to gravity, split things in X and Y, hopefully all this stuff is familiar. And reminder to you all, if you are moving, or let me rephrase this, if A is 0, that does not mean you're not moving. If A is 0, that doesn't mean you're not moving. It just means you're not speeding up or slowing down. An you shoot something in space, that thing will be moving after it leaves whatever it gets shot out of, but its acceleration will be 0. So let me make up a random problem with this. This is the problem that people missed on the test, was draw a free body diagram for something getting tossed to the air to the right. So let's see. What do I want to make this one? Draw a free body diagram for what would be an equivalent one? For a rocket pointed straight down in the air. Do not ignore air resistance. The rocket is on, to clarify. A rocket pointed straight down. Yeah, the rocket's on. I wouldn't call it a rocket if it wasn't pointed straight. With its engines on. Oh, it is on Earth. If it's pointed straight down, it's got to be pointed. And it's on Earth. It's not super far from the Earth in space with nothing around. See, this is why test problems are really hard. Like, it's hard to make a good problem because I have to make sure and I give you enough information without, like, giving away kind of, like, certain things. Yeah, it gets really tricky. I have to give enough. But I also don't want to make the problem an entire paragraph. So, there's a rocket. Super aerodynamic. And you just go through the checklist. Is it a string attached to it? Is there tension? No. Is there anything pushing or pulling it? Yes, there is an applied force pointed straight down. That's the rocket. FA generally means force applied, not force air. An applied force is just anything that's not explained by everything else. Something pushing, whatever, stuff like that. All right, is there gravity? Yeah. There is a force of gravity. Is there air resistance? Yes. Air resistance is always opposite the direction of motion. So, if I'm going downwards, friction force is upwards. Is there a surface that I'm touching? Is there a normal force? No. This rocket is not sitting on any surface nor leaning against any surface. And we've gone through our whole checklist, and that's what we get. So that's what you do with these. You just go through the checklist, which might feel kind of memorization-y, but you add them to your paper if you think you'll forget them. There's like 5 or 6 of them. They're all listed right here. If you're like afraid of forgetting them, there they are in all their glory. Just copy and paste that and put it on your paper or something. The beautiful thing with physics, I don't care about the memorization. I care about can you apply it. So, great. So there's that. Lots of fun. Yeah. Try these ones out. A car is going in a circular path with a radius of 10 meters. And I don't want you all to try to solve this whole problem. We don't have the time for you all to you can if you want to. Feel free to try to solve the whole thing right now. For the sake of time, I'm just going to give you all like a minute to just see if you can think about how would you solve these? How would you set this up? What concepts would you use? That kind of thing. And then I'll start solving it out. Unfortunately, we don't have the time. If you do want, this morning I had the studio class, and that has pauses in it. So if you all want to go through these, the studio class went through the exact same stuff. There's a lot more time. You can practice these things and whatever. All right, so for the first one, y'all, a car is going in a circle. If you ever see something going in a circle, a little tiny light bulb should turn on somewhere in your head that says, I should consider centripetal force. You're not always going to use it, but it's one of those things that you should remember that it's a tool that exists. In this problem, we're going to use it. Anything going in a circle, you just need to remember centripetal force is an option, is a tool. Have a little light bulb that turns on. Remember that that's something you can use. So we got our car going in a circle with a radius of 10 meters. So to that end, centripetal force says that centripetal force equals the sum of forces pointed away or towards the center positive, away from the center negative, as long as it has a component of it. All that jazz. Centripetal force is mv squared over r. The only force acting on this, and it doesn't even say the word force in this, so that's why it's not a giveaway. You just have to practice these problems to realize. That's why I said if it's ever going in a circle, you just have to have that little light bulb come on in your head that centripetal force is an option. Because it's not obvious in this problem that we're going to use this. It does not mention force anywhere in this problem. All right. But the only force acting on it towards or away from the center is centripetal force, which is mu Fn. So we get mv squared over r equals mu mg. M cancels. We have v, we have mu, we have g, we have r. We're solving for v. No, we don't have v. We're solving for v. So v equals the square root of mu g r. And you plug in the numbers and you get that answer, and it's great. This is you can then think about what would change. If the road was slippery, what would change? Mu would go down, so my velocity would go down. What if I made my radius bigger? Then that would mean I could go faster. So you can kind of see some interesting results from this in terms of practical applications that make sense. You all know if the road's slippery, you can't go as fast and stay on track. You all have hopefully seen that when you take really tight turns, it can feel a little hairy, and your car may feel a little bit more uncertain. This all matches reality. That's always something you all should do. All the physics you're learning, especially Physics 1, you've been living your whole life around this. Physics 2, I'm going to warn you, is going to be a little bit trickier for you all to do that because it's stuff you can't see. You can't see electricity, so still try to make those connections, but just be prepared for that to be a little bit more challenging. Last thing I do want to point out with this, has nothing to do with this problem. The reason big semis and stuff have to be careful is because of torque. If a semi is really tall, it's going to want to rotate. It's going to want to fall over. So if your vehicle is really tall, you can't go as fast, and it's not explained by this. It's explained by torque, which is why we need to cover torque. All right, great. Next one, 500 kilogram car starts at rest, accelerates to 20 meters per second in 5 seconds. If the force, immediately if you see the word force, draw a free body diagram. Due to air resistance and friction is 300 newtons. What is the force pushing the car forward? We immediately draw a free body diagram of gravity down, normal force up, applied force, that's what the engine's doing, and friction force. My arrows are not at all accurate to the size, but it gives you a sense of all the forces. Then we remember the sum of forces equals MA. The sum of forces in the X equals MAX. The sum of forces in the Y equals MAY. Yeah.
What is the sum of the forces in the Y direction be 0?
It will be, which is actually very important for us solving this. That's a great point. So what the question was, isn't the sum of force in the Y direction 0? It is. In this problem, this car we're assuming is not flying up into the air nor plummeting down to the ground. So in this case, if we set this up, that's going to be 0. But this is important for us to actually solve this problem. So we're going to get Fn minus Fg equals 0, which in this specific problem means that Fg equals Fn. That is not always true. There is cases where Fg does not equal Fn. You can't just assume that in every single problem in this expression. If the acceleration isn't 0, if you are moving upwards or downwards, then it's not going to be the case. Remember the whole elevator thing. So when we look at the x, though, we have FA minus FF equals m times A. So we are looking for the applied force, and that's going to equal the mass, which is 500, times the acceleration, which is going to be the change in velocity over change in time, 20 divided by 5. And then we are going to add the friction force, which is 300. So actually, sorry, in this case, you all didn't need to know that expression at the bottom. But if I instead said that the force of friction is 300, if I instead just said find the coefficient of friction, if I gave you like how much it was pushing forward, I can say find the coefficient of friction, in which case you need to know Fg equals Fa and all that. So there was examples where that kind of got chucked in. Here you're spared because there's air resistance. And the answer is 2,300 newtons. The most common mistake on this problem is people instead subtract these numbers. They'll do 500 times whatever, 4, and they'll get 2,000, and they'll subtract 300 and get 1,700, and it's wrong. Very sad. So you got to remember, pluses and minuses, they'll get you. Most of the mistakes you'll make will be pluses or minuses, and for whatever reason, it's also really common to be off by a factor of 2. So just be ready for that. It's just a thing. That was always, when we were in grad school, it was always a thing. It was, where did that factor of 2 came from? Basically became a meme because of how many times we asked it to each other. It just shows up so much. All right. This one, again, for the sake of time, I'm just going to remind you all the trick, and then we'll move on. This is from test 1. Jill passes Bob at stoplight. Jill's traveling at a constant velocity. Bob's initially at rest, accelerates. How long will it take? You go through all the rigmarole. You write all the givens, the missing. And the trick to this one is remembering that their final positions are the same. Their final velocities are not the same. This was the most common mistake on this problem, is people solved it by saying their final velocities are the same. You will never catch up to something if you go the same speed as them. You have to go faster. In fact, if you do the math here, you find out Bob ends up going like 40 meters per second, which ends up being like almost 100 miles per hour, which is a little stupid fast. Cars can do it, so it's fine, I guess. If you're constantly accelerating, you get real fast, real quick. To show the expanse, that's how they get around. That's how they make fake gravity, too. They stack their spaceships where the floors are... Anywho, you can make fake gravity by just having a constant acceleration of exactly gravity. It'll feel like gravity. You can get places really fast in the solar system if you can accelerate constantly. The problem is fuel is expensive. So that's really the challenge to getting anywhere fast in the solar system, is fuel ain't cheap to get up there. So, anyway. All right, this part B is just more the same. The answer to that one is 2,500. It's just like the problem we just did, so I'm not going to bother with it. There's the answer. You can do it for yourself. It's just like the last problem we did. All right. I think this is the pulley one. I don't know where the pulley picture went, but if you all look at the one that's uploaded, it's the whole pulley with the block and the thing. Yeah. We love that problem, right? So feel free to check out that one in the past. I'm not going to, for the sake of time. That one's been solved somewhere. All right, let's see. In my remaining 30 minutes, what do I need to convey to you all? So I spent a lot of time on test 1 review. And the reason I spent so much time on test 1 review is because it literally was the longest to go. Test 1 was 2 months ago, more maybe. Test 2 was literally less than a month ago. Test 2 was on November 12th, I think. It was literally only 2 weeks ago exactly, which is wild. Something like that. So, hopefully that's more fresh in your mind. I expect test 1 to be less fresh in your mind. This is also a good opportunity to give you all some perspective on how difficult in air quotes, the challenge level of the final Just looking at my grades from the spring, so I taught 2048 in the spring, very similar in a lot of ways. Test 1, people scored about a 7. Yeah, I'll just give numbers. Test 1, people scored, I think, like a 68. Test 2, people scored like a 74. And then the final, people scored a 71. What's the benefit of that? Long story short, the final is basically halfway difficulty between test 1 and test 2. So I expect in your all's case it to be basically the same. So take the difficulty of test 1, take the difficulty of test 2, and the difficulty of the final will be somewhere in between those two, which makes sense because they make up most of the tests. It's literally the average difficulty of the two tests we've done. Which is really nice that it ended up that way in the spring. So to that end, that's what I encourage you all. If you all felt like test 2 was easier than test 1, great. If test 2 didn't go well for you, spend time on that. But you all did pretty good. Like test 1, you all averaged 72 or something like that. Test 2, you all averaged like a 75%. So I'm expecting the average for the final to be like a 74%-ish, something like that. So there you go. Give you some perspective on that. Okay, these ones, same thing. I'm just going to give you all a few. So let's just quickly recap what the heck we learned on test 2. I'm just going to blitz through this. Energy. You got energy. Great, right? This is the thing that you all really need to be very, very comfortable with. Energy initial plus work equals energy final. If you are not cool with this equation at this point, then get familiar with this equation at this point. Work is how much energy you gain or lose. If it's positive, you gain energy. If it's negative, you lose energy. There's 4 types of energy. On the test 2, there was only 3 types. Now you got an extra one. You got spring potential energy, gravitational potential energy, translational kinetic energy, and rotational kinetic energy. Here they all are, or at least 3 of them. Here, I'll chuck the last one in here. Rotational kinetic energy. It's the same as translational. You just make the swap. 1/2 I omega squared. Unfortunately, these I's look like L's, but such is the nature of some fonts. Units, joules, fantastic. Second half of the test is momentum. Add up all your momentums at the beginning, they equal all your momentums at the end. It's a great time, super straightforward. You all did really, really good with this stuff. And then, yeah, there's universal gravity and center mass. Again, hopefully all of this, it was literally like, we reviewed this 2.5 weeks ago, so that's why I'm just blitzing through it. But I do want to point out some things. So the reason I'm blitzing through this is because I do want to spend time. You all did not get this problem. My studio class did. And I want to point out something with this because there was a really common mistake that people that chose this problem made. So you got a sailboat. It's traveling initially with a velocity vector of 4I plus 6J. There's a force of wind on it at 200I plus 150J newtons over 2 seconds. What will be the magnitude of the sailboat's velocity after the 2 seconds? And then part B, how much work did the wind do? What I want to point out in this problem is that velocity, forces, acceleration, those are vectors. Those are vectors, and we work in components, x, y, all that jazz. Energy, work, is a scalar, and you should not work in x and y components when you're working with energy. If you work in x and y components, you will get the wrong answer. And the reason for this, how much work did the wind do? If you remember, I'm going to use the phrase conservative forces and non-conservative forces. So I gave you all the problem way back when where I said, I go this way, I make this winding path, or I make this really long path. In which case did friction do more work? And the answer was the long and winding path. There is forces where you care about the path you take. You all know this. Pushing a box on a floor a long distance is exhausting. Pushing it a short distance is not as exhausting. You all have experienced that. The weird one is that gravity doesn't care about the path you take. Gravity, you don't care. There's conservative forces that don't care. But friction, air resistance, wind, pushing something, they care about the path. If, on part B in this problem, you work in vectors, work in components, You are saying that the wind pushes the boat to the right and then it pushes it up. And that is not what happens. The boat does not make a straight line to the right and then a straight line up. It does some really complex path, actually, because it's a force involved and all that kind of jazz. So the question is, how do you solve this? So I'll do one problem at a time. So part A is actually very straightforward. There's two ways to solve it, and they're actually the exact same way, just with different paint jobs. Why is it going to speed up? Because there's a force. So what? Forces result in acceleration. So F equals ma. So A equals F over m. So you can find the acceleration in the x and y direction. And then with that, you can do the, easy peasy, VF equals V naught plus AT. And you're going to do that in x and y. And it'll be great. And you'll have so much fun. That's one way. The other way, which is the exact same way, it just looks different, is that I taught you all that impulse equals the change in momentum. That was an equation. It's on your formula sheet. Let's just rewrite this. F times change in T equals M times change in V. Our mass is not changing. Our sailboat's not breaking into pieces, so mass is a constant. We can pull that out. Rearrange this. You get F over M equals the change in velocity over the change in time. It's literally the same thing as the other side. Impulse is just another way of writing Newton's second law with the kinematics sprinkled in. F over m is A. A equals change in velocity over change in time. So the momentum impulse stuff is literally just Newton's second law with a different paint job. Looks a little different, but it's the same thing. Great. Y'all can try it out. It's a great time. Good problem. Part B. Part B is actually very, very simple if you realize I don't work in components. How much work did I do? And there's basically two equations for work. You have option A, which is Ft cosine theta, where you will have to find the force. That's fine. You can find the magnitude of force. You would actually have to find the distance that you traveled, and this is a crazy path, y'all. Like, you'd have to plot the path that this sailboat went, and there's a force acting on it, which means it's acceleration, which means velocity is changing. And look, I have no idea what this is going to look like, to be honest. Like, I don't know. The force, maybe some parabolic path kind of thing. Good luck finding the length of a parabolic path. Gross. Or, so that's unpleasant. Or, energy initial plus work equals energy final. You say, what energy did I start with? I started with kinetic energy. So let's rearrange this. So work equals energy final minus energy initial. So work equals, what energy do I end with? Kinetic energy. What energy do I start with? Kinetic energy. The only thing you got to be careful of here, you have to do the magnitude of these velocities. Do not put the x and y component. Do not do this problem in x. Do not do this problem in y and then combine it. It doesn't get you the right answer because you're then saying the boat goes to the right and up, and that's not what happens. So, if none of that made sense, this is the takeaway I need you to know. Vectors break into x and y. Scalars do not break into x and y. That's what I need you all to know, and that will carry through in all your future classes. Vectors, you need to break into components. Scalars do not break into components. Do not, just do magnitudes. Whenever you're working with energy, magnitudes. Whenever you're working with forces, x and y. Okay? That's the main punchline if nothing else made sense. So, it's a really, really common mistake. I train you all and I tell you all, break into components, break into components, break into components when appropriate, when you're working with vectors. Scalars, you don't need to make your life more complicated. All right. Great. The spring problem, fairly straightforward. Like, you all did pretty good on this one. This is just energy. This is the one. Energy initial plus work equals energy final. In this case, work is 0. Second one, energy initial plus work equals energy final. In this case, work is not 0. Find it. Really straightforward. Lots of examples of this. Work here just equals -2. And we start with, I could just set this up real quick. It takes 5 seconds. We start with spring energy. And we end with just potential. This one, we start with spring energy. We have our -2, and we end with potential. We assume at the highest point it's not moving. Great. So fun. That problem. All right. And then just a very, very quick recap of what I taught you all this last week and a half, which hopefully is very fresh in your mind. Ooh, and yeah, the reward for you all sticking around is I'm going to point out something on the quiz that most people will make a mistake on. It's not a typo, but it's a really common mistake that basically, I'm going to say conservatively, at least 50% of people will get this question wrong in a quiz because, well, you'll see why. All right, great. So we'll get to it. Every single translational variable has a rotational equivalent. Force becomes torque. Mass becomes I. X becomes theta. V becomes angular velocity, blah, 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 all the things. Translational variables just multiply by R. Multiply the rotational one by R. Talked about that a bunch. Right-hand rule. Do not forget, y'all, that how do you find the direction of torque? If you have some lever arm and you have some force acting on it, R points away, F points up. You swing your hand, and in this case, torque is out. Also, remember to y'all, angular acceleration is the same direction of angular velocity speeding up, opposite direction of slowing down. This is just the same thing. If velocity is to the right and acceleration is to the left, you're slowing down. If velocity is to the left and acceleration is to the left, then you're speeding up. Great. Smash that into your head a bunch of times. All right, kinematics equations. Again, I'll upload all these slides. So like if you're like, man, he's going so quick, they'll be uploaded. Rotational equations are just the translational ones with a new paint job. Change all the variables out. V becomes omega. Theta becomes X. A becomes alpha. It's wonderful. Moment of inertia, different objects. Here's the main thing y'all need to know. The farther away the mass is from the axis of rotation, the harder it is to accelerate angularly. The harder it is to spin faster or slower. That's pretty much the major thing I hope you all know about a moment of inertia. The math is whatever. If you understand the concept, that'll get you most of the way there. And parallel axis theorem is great. We did some problems with that. Check it out. So much fun. All right. Now we've gotten to the one where I can finally tell you the quiz problem that most people missed. Torque. It's force. It makes things accelerate, but in a circle. It makes things angular accelerate. Whether that speeds it up or slows it down is a matter of which way you're moving to begin with. The problem on the quiz, if you haven't started already, if you did, great. Nothing wrong with that. Just to remind you all, the quiz is due literally the Wednesday before the exam at midnight. It's as late as I can make it. The plan is, so you only have 2 assignments left, the quiz and the final. That's it. All of the grades are in at this point. You all can use that spreadsheet to calculate what you need to get on the final. That exists. Use it. It'll either give you peace of mind or more stress. I don't know. So up to you. After the final on Thursday, my goal, we'll see if this manifests the way I hope it to, is on Friday to have all the grades in. Your final grade, because it's multiple choice. I just scanned them all. It's great. Have all the finals scanned. Go through and calculate your grade. See if it replaces your lowest test grade. And I'll try to update all that. Go through it and calculate whether clicker questions benefited you or hurt you, and then modify things based on that. The goal is that by the end of Friday, you will be able to look at web courses, not this week, obviously. Friday, December 6th, the goal is by the end of that day for me to send out an announcement and say the grade in Canvas is the grade you have. Look it over and let me know if there's any mistakes. Whatever the grade is, will be what it is. Like, I will only change things if there's a mistake. I will not give any extra credit. I will not give any additional assignments. I will not open any old assignments. None of that. I will only make changes if there's an error. And I will round your grade up I will round it up to the nearest whole number. No matter what. So if you have an 88.9, it becomes an 89. If you have an 89.1, it becomes a 90. If you all look in the syllabus, If you have an 89 or above, you will have an A. Now, when I say, so an 88.9 will be a B, to clarify that. So you have to have above an 89. You have to have above an 89, because it always gets into rounding. People are like, I have an 89.4, so I just round everything above an 89 up to a 90, and that's it. This is all in the roof. This is all in the syllabus. If you have an 88.9, I will not round it to an A, because I'm already adjusted my rounding. I've already increased it more than what traditionally is. So anyway, this just heads up, great things. People like that information. So anyway, that'll happen on Friday. You'll point out things. Grades are literally due on Wednesday the 11th at noon. I have zero control over that. So on Tuesday, I will submit the grades. I am not going to wait till Wednesday. I am not a person who waits till the last hour to submit things because I cannot guarantee. It's always a bad idea to wait till the last day to do anything. You never know if technology is going to work. You never know what's going to happen. You never know if I'm going to get sick or who knows what. I'm going to submit grades to my UCF on that Tuesday, and I will notify you of such. I will say by Wednesday at like 4 p.m. or something like that. I'm not going to do it at midnight because I'm not waking up at midnight. So anyway, you all will have over the weekend and Monday to let me know if there's mistakes. Great. There's updates on that. Let me show you all the problem that over 50% of people are going to get wrong, at least in the first attempt. The problem says I don't know what it is in the problem. Let's just say water bottle. I hold a water bottle up at an angle of 30 degrees. The water bottle has a mass of 1 kilogram. I don't know what the mass is. I'm just making up numbers, but my arm is massless. I could have made the arm have mass and it would have been fine, but I made your life a little bit easier. So my arm is massless. There it is in its spaghetti goodness. R here equals 0.6 meters. I think that is actually the number in the problem. That's a reasonable arm length. And it says find the torque. And again, this angle is, I don't know what. I'm just going to call it 20 degrees. Pick whatever number you want. Find the torque acting on the shoulder joint. That's where the torques always act on the wherever it's rotating. Your shoulder is upon which things rotate. So, find torque. I'm going to give you all a couple moments. And then I'm going to tell you what the answer is not. The answer is not 2.011. That is wrong. And I'm going to give you some time. If you thought it was that, I'm going to give you some time to see if you can figure out why before I give you the magic reveal. You are going to use torque equals RF sine theta. This problem is solving this problem is simple if you use the right numbers. And if you draw your picture well. Force of gravity is downwards. Fantastic. No surprises there. So this problem is very straightforward. It is R times F times sine theta. R is 0.6. F in this problem is going to be 1 times 9.8. The angle that you're going to put in this equation is not 20 degrees. And this problem is a reminder to you all that just because the equation has theta in it does not mean that the theta I give you is that angle. That's something that you don't want to fall into the trap of. Just because I give you an angle doesn't mean it's the angle that's in the equation. So you always need to think about whenever you're using an equation what these variables correspond to, and don't just assume it's the thing I give you. This is the angle between R and F. The angle in this equation is the angle between R and F. So if you extend R a little bit, it makes it a little bit easier to see. This is theta. This is the angle we care about. And again, this is a good I like this problem because it's not supposed to be a trick problem. The goal is not to trick you. The goal is to make certain you're being careful and you don't just take the numbers I get you and chuck them into whatever equation. So, I'll give you all a few moments. What is the value of this angle? This is a really useful skill to be able to take an angle and then find a different angle in the picture. You're going to be doing it a heck of a lot as engineers. So there's a few ways to discover this. There's two ways that I've kind of figured out. One is that you all can see that this is a right triangle here. So this angle is going to be 70. And if this angle is 70, this is a straight line. Supplementary angle is 180 minus 70 is 120. The other way is, if you all realize that, and this is where it gets a little tricky to show because I just didn't give myself enough room. If I make this a bit bigger, this angle is 20, and then you have a nice right triangle here, and 20 plus 90 is going to be that 110. Yeah. So, and I misspoke before when I said it was 120. So it's 110. So theta is going to be 110 degrees. And sine of 110 is not the same thing as sine of 20, and the unit circle is really handy to show this. So unit circle, the y component of the unit circle is the sine. So 20 degrees gives you, about there. So this is sine of 20. It's how high up you are there. Sine of 110 is up here. And you can see that those y heights, it's kind of good to, I don't know. Unit circle helps me understand why angles are what they are. It's a picture. So you get sine of 110, and that will get you the right answer. It doesn't matter what it is. It just matters that it's not the one that you might have thought it was. You can also do sine of 70, and that gets you the right answer as well. Sine of 70 and sine of 110 are the exact same value. You can see that from the unit circle. Sine of 70 is that over there, but so the torque equals 5.52. And we can think through the logic. Does this make sense? Which one's going to be bigger? All that jazz. Torque is all about finding the part of force that is perpendicular to the motion. So the more vertical my arm is, the less torque there is. If my arm's straight up and down, my arm's not going to spin. It might, want to collapse, but it's not going to spin. And then when I'm like here, it's not that hard to do. It is the hardest to hold something when it is exactly horizontal to you because the torque is exactly, the force is exactly perpendicular and all that jazz. So, good stuff. So if you're ever unsure which angle it's going to be, it's going to be one of those. You either know it's going to be sine of 20 or sine of 70. Which one makes sense? Which one's going to be harder to hold? Just think about your experiences in reality and all that jazz. And that's that. I mean, at this point, rotational kinetic energy. That's, look at all these things you learned, y'all. Stuff you knew, stuff you didn't. Yeah, it's a good time. Enjoy Thanksgiving, y'all. Take it easy. Give yourself some break. Don't just go, 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 go. It's not healthy. And yeah, I'll see you all next Thursday. It'll be or office hours, whatever you decide to come to. And you'll be done. After next Thursday, you'll be done with my class.